This video is going to discuss Dirac notation for matrices, which is Dirac notation for discrete cases. So in this case, we're going to have, as we had for a given vector, we're going to have a set of basis vectors, which are going to be unit vectors indicated by this caret hat on top of EI. So they're going to be n basis vectors for our n-dimensional vectors. So in Dirac notation, we're going to have this particular, we have a vertical bar, and then I, and then a kind of closed bracket there. And that's going to represent a particular basis vector. This particular type here would be a ket vector or a ket. So I would be somewhere on the scale between 1 and n, being an integer, representing one of these individual basis vectors. So if our basis vectors are represented by these little ket vectors here, we can represent any vector in that many dimensions as vector A, which is also represented as a ket vector for sum from I equals 1 over all the dimensions of the magnitude in that dimension, AI, times basis vector I. So all these coefficients here in general are complex numbers, but will often end up just being real numbers. As I said, A can represent any vector in n dimensions with all of these basis vectors. And if that is true, then the set of all of these basis vectors, all set of all these kets I, is said to be complete in n dimensions. Complete means we can represent anything in that many dimensions. All right, so this vector, this ket vector, is equal to a vector just as we defined in the first video of this playlist. Can also be represented as a bold letter A or a single underline for a one-dimensional tensor or rank 1 tensor. So it's going to have n elements in general, being an n-dimensional vector. But we can also do this that we have here, where we have the pointy part with a pointy bracket on the left, and then the vector, then a vertical line. And this is the adjoint of that vector, which is the complex conjugate of that vector, and it is a row vector where all of the elements have been taken to their complex conjugate. So this particular vector is called a bra or a bra vector, and the two combined, you might have noticed with the given ket name, are going to be bracket or bracket notation. So that was a rather clever idea, perhaps, to call certain vectors kets, certain vectors bras, get bracket for notation because they kind of form a bracket between the two of them. Okay, so we can define this next type of symbol, which is we have the bra vector on the left and ket vector on the right, which is equal to the adjoint of A times B, which is equal to the dot product of A star and B, which is equal to this row vector, column vector multiplication, which is equal to their dot product formula, the sum from I equals 1 to n of A star I times BI for all of the individual elements until you get to n. So as we said, for two given vectors, this is called the scalar product, inner product, dot product, whatever name you prefer. They all mean the same thing. So given a particular bra vector with its own ket, that is going to be the magnitude squared of that particular vector, the sum over all of its elements, A star I, AI. Note that for a given complex number, A star I times I, a number times its own complex conjugate is the magnitude squared of that complex number. So its magnitude summed over all of the elements is going to be the magnitude of all of the elements or the magnitude of the total vector. Okay, so we can represent each bra and ket in its given basis of bracket vectors. So A is sum from I equals 1 to n of A star I, bra I. Ket B is equal to sum from j equals 1 to n of component B sub j times ket j. So if we use the formula for what this inner product is of A and B, we get this following sum over I, sum over j, A star I, bj, and then the inner product of basis vector I and basis vector j. And we know from the definition of what this is that this also has to equal this. So if we factor out what the inside terms, what we're left with is the sum from j equals 1 to n of b sub j of the inner product of I and j is equal to bi, which is equal to the sum from j equals 1 to n. I think I just wrote that again there. Doesn't make much sense. But anyway, what this ends up implying, if we stare at this long enough, is that the overlap, or the inner product of I and j, has to be the Kronecker delta. It has to be 1 if I and j are the same, and 0 if I and j are different. And this is the definition of an orthonormal basis set. It's normal because the inner product of a vector with itself is 1, and it is orthogonal because the inner product of a vector with another vector is 0. So if this is I, then this is 1. So it's normalized, and if it's ij and they're not the same, it is 0. All right, what about the inner product of a bra basis vector with a ket vector? So this would be sum over I equals 1 to n of ji, and then the coefficient ai, substituting in there for what the representation of a is. So we know that this is delta ij, so this is sum over I, delta ij, a sub I, which is equal to a sub j. So this means that the coefficient a sub j that we're representing one of these coefficients of our vector, that vector is the inner product of basis vector j with vector I. And then the complex conjugate of that is if we flip which one is the bra and which one is the ket. So if we do this derivation in reverse, we get that a star j equals aj, whereas aj equals ja. So this implies that in general, the complex conjugate of an inner product is reversing the bra and ket of which one is which in that inner product. Okay, so looking at this, we also see that since a sub I is going to be equal to ia, that particular vector, we can represent a as the sum from I equals 1 to n of a sub I times basis vector I, which is equal to the sum from I equals 1 to n of a sub I equals ia, the inner product there, times basis vector I over all of the vectors. And we know that a has to equal a, so the result is that this part here has to equal 1. So 1 is equal to the sum from I equals 1 to n of the ket of I times the bra of I. So what this is called the resolution of the identity, and we're going to use this in future videos to derive how we're going to change basis sets. We noticed that these were a set of basis vectors, but it's arbitrary what we can use for our basis vectors. There are infinitely many different choices we could choose for our basis vectors. So if we want to change from one set of basis vectors to another, we're going to use an expression like this, which is called resolution of the identity. So this video in general is getting into some of the more advanced topics which are going to be useful for a lot of the advanced molecular quantum mechanics and electronic structure theory, things like Hartree-Fock, Mahler-Implicit perturbation theory, etc. But the basis of Dirac notation is going to be used a lot throughout that playlist because it's very convenient to express things quickly. It's much quicker to write things in terms of bras and kets than writing them out in terms of their individual vector components.